Let me welcome you to this lecture. We have been discussing the chemistry of group 14 elements, and so far we have discussed about different types of compounds formed by carbon. We have discussed about the allotropes of carbon, as well as we have discussed about the metal carbides, carbon oxygen compounds, and in the last lecture we have discussed about the compounds formed by carbon and nitrogen. So during this lecture, we will discuss about uh, compounds formed by silicon with oxygen, that is compounds containing SiO linkage. As such, the silicate minerals or the aluminosilicates and silica, which is sand, these constitute 95% of Earth's crust. So these silicon, oxygen, and aluminium are the three most abundant element on Earth. And if we look at different uh, geological materials like rocks, then sand, as well as clays and soil. So these clays and soil are the breakdown products of rock and sand, and these are essentially all silicate minerals. And again, many of these construction materials like the granite or the bricks or cement also, these are all silicate uh, minerals. And apart from that, we the ceramic and the glass that we use are also silicate minerals. So ceramic and glass, these are all silicate minerals. So what we have seen is that silicate or silicate minerals or compounds containing silicon, oxygen, bones are very important, as many of them have a lot of important applications. So during this lecture, we will discuss about different types of silicate minerals and how we can classify these minerals based on their structure. So, so there are soluble silicate minerals are there, and that is you can make soluble silicate minerals by reaction of sodium carbonate. Sorry. When you heat at around temperature 1400 degrees Celsius, you will break it down into carbon dioxide and sodium oxide. Now this sodium oxide, which is basic in nature, is going to react with silica, which is an acidic oxide. So then what we form soluble silicate minerals like Na4, SiO4, or as well as Na3, SiO3. And so this sort of plus other sodium silicates as well. So this mixture of compound that is formed is essentially soluble in hot water. And millions of tons of this sodium silicate is produced each year because they have very important application in liquid detergents. And these are used to increase pH, because then only you can dissolve grease or fat by making soap, and that is why they are used in liquid detergents in order to raise the pH and thereby dissolve the fat or grease that is there as dirt. So this is one major application of soluble sodium silicate here, and that is why it is produced in million of ton every year. Apart from that, it is also used in adhesives, fireproof paint. So in all of these applications, again, sodium silicate, which is soluble, is used. So this is one example of soluble silicate. But majority of silicate minerals, as we have seen, different types of silicate minerals like rocks, clays, sand, or the building materials, construction materials. These are not soluble minerals, or these are not soluble in any solvent, and these are essentially most of these silicate minerals are insoluble. So, and the reason why these silicate minerals are insoluble is because in these cases the silicate, the SiO4 4 negative group essentially undergo polymerization by sharing some of the oxygen atoms, and that is how it forms infinite extended solid structure. And these SiO bonds are again one of the strongest known bond, and that is why when we have extended structure formation through these SiO bonds, the resulting solids are highly insoluble in nature, and that is why we have the silicate minerals form the rocks or sand or clays, these sort of materials. So majority of silicate minerals are essentially insoluble in nature, and if we look at the structure of these silicate minerals, we there are certain key points that we can learn. One of that is that the first one is that the difference in electronegativity between silicon and oxygen is equal to 1.7, and this essentially implies that the SiO bond is 50% ionic and 50% covalent. So it is both ionic, and the ionic character is equal to the covalent character for the SiO bond. Then what we see, if we look at the structure of these silicate minerals, what we will see is that these are essentially these are constituted uh, either discrete SiO4 4 negative tetrahedral units. So we have SiO4 4 negative tetrahedral units. So that this is, we can draw the SiO4 4 negative tetrahedral unit in this way, or so either discrete SiO4 4 negative units are present in these silicate minerals, or polymeric structures formed by sharing oxygen atoms on the corners of the tetrahedron. So see, the oxygen atoms can be shared by two SiO4 units, and that is how, say, this is how we can have extension So in this way, the SiO4 units may get connected by sharing oxygen atoms. Here we have seen how we can connect two SiO4 units through one oxygen atom. So they share one oxygen atom, these two tetrahedral SiO4 units, and that is how the polymerization of SiO4 units or tetrahedra can occur, and this is how majority of silicate minerals structure essentially is formed by sharing of oxygen atom of these SiO4 units. So we can have either discrete uh, SiO4 units in silicate minerals, or else we can have uh, polymeric structures which are formed by sharing of oxygen atoms in of these SiO4 tetrahedral units. So the fourth important structural point about these silicate minerals is that the oxygen atoms form closed packed structure. So when they form this closed packed structure, essentially what happens is that this means that in the structure we will have octahedral and tetrahedral holes are present, and therefore tetrahedral and octahedral holes are present. Now, different metal ions, depending upon their size, may either occupy these tetrahedral or octahedral holes. So, these silicate minerals, the metal ions essentially reside in either tetrahedral or octahedral hole, depending upon the metal ion. So, the which particular hole, whether a metal ion can occupy a tetrahedral hole or an octahedral hole, is dependent upon the size of the metal, and that is why one particular metal ion can occupy either tetrahedral hole or it can occupy octahedral hole depending upon the size of the metal ion. But they cannot switch between two types of holes here, tetrahedral and octahedral. So these are some of the key points that we can learn by looking at the structure of the silicate minerals. Now we will see how we can classify these silicate minerals based on their structures. So the first classification or first type of structural type of silicate minerals that are present are known as orthosilicates. So in case of orthosilicates, discrete SiO4 units are present. And the SiO4 units do not share any of the oxygen atoms because they are present as discrete SiO4 units in case of orthosilicates. Examples of orthosilicates we can have divalent metal ions and as well as we can have trivalent metal ions. Tetravalent metal ions. In this way, examples of divalent metal ions here are beryllium, magnesium, iron, manganese, zinc. So for all of these metal ions, these sort of orthosilicates are known for divalent metal ions. Similarly, for tetravalent metal ion, we have one example where zirconium is present. So this particular orthosilicate, that is SiO4, where zirconium is a tetravalent metal ion here. So this particular orthosilicate mineral is known as zircon, and it is used as a gemstone because it looks like a diamond, and that is why it is used as a gemstone. But it is quite cheaper as compared to diamond or real diamond, and that is why it is essentially a cheap gemstone as compared to diamond. Then we also have another type of autosilicates, which is where mixed valent metals are present. So both divalent and trivalent metal ions are present here. So we have SiO4. So this we have 2, and this is 3, and this is going to be 6, and this is also 6. So this is going to be equal 3. So this is how we can balance the charge here. And when the divalent metal ion is beryllium and the trivalent metal ion is aluminium, this particular autosilicate mineral is known as beryl. Again, this is also beryl is also a gemstone, and when we have beryl with 10%, 1 to 2% chromium impurity is present in beryl, then the gemstone which contain this 1 to 2% of chromium impurity is essentially known as emerald. So what we have seen that there are 3 different types of autosilicate minerals here depending upon the metal ions. We have 3 different types of autosilicates, one where divalent metal ions are present, one where tetravalent metal ions are present, and in one case where we have both divalent as well as trivalent metal ions are present. And we have seen examples or important examples of this type of autosilicate minerals, and we have seen that many of these are essentially used as gemstones. Now when we try to draw the structure of these silicate minerals, we essentially follow a conventional method because the silicate, the SiO4 unit is tetrahedral in nature. So if you look at from the top of the, if this is your eye over here, from the top of the silicate ion over here, through this oxygen silicon bond here, what you will see is a triangle. For the 3 oxygen atoms here, these 3 oxygen atoms, say 1, 2, and 3, will essentially form the base of the triangle here, and this oxygen atom over here is going to be on top of this triangle, and the silicon atom is going to lie exactly below this top oxygen atom over here. So then we can draw this silicate ion or this SiO4 4 negative unit in this way. We can write, and this will help us or assist us in trying to draw the structure of different types of silicate minerals which are formed by sharing of oxygen atoms of this SiO4 unit essentially. So that is why we will draw the SiO4 4 negative unit in this particular fashion. So these are the oxygen atoms. These oxygen atoms, so we can again label these oxygen atoms 1, 2, 3 essentially will appear in this way if we look from the top over here, and this oxygen atom, that is O4, is going to be here, and this small this solid circle in the middle below the central oxygen atom over here is essentially the silicon atom. So that is how, this is the conventional way of drawing the SiO4 4 negative unit, and we will follow this method in order to draw the structure of different types of silicate minerals. So let us now see what other types of silicate minerals are formed when we have Apart from this orthosilicate, where there is none of the oxygen atoms are essentially shared, by sharing of oxygen atoms, we can form what different kind of silicate minerals. So next one is pyrosilicate. So it is formed by sharing of one oxygen atom per SiO4 4 negative tetrahedra. So when we do so, we have already drawn this structure earlier, but now we will draw by using the conventional method to draw the structure of silicate minerals. So let us draw. So this is one tetrahedra. So it is going to share only one oxygen atom with another tetrahedra. So let us draw the other tetrahedra as well. So this is how we can join two tetrahedral SiO4 units by sharing one oxygen atom, and the kind of silicate minerals formed by sharing of one oxygen atom of this SiO4 unit are known as pyrosilicates. So the formula is going to be Si2O7 6 negative. That is going to be the formula of pyrosilicates, and one example of pyrosilicate is essentially scandium Si2O7. This is one example of pyrosilicate, but as such pyrosilicates are quite rare, and this is one example where pyrosilicate ion is present. So this is how we can draw the structure of pyrosilicate ions, and this is how the pyrosilicates are essentially formed. So the next type of next structural types of silicate mineral are known as cyclic silicates. So when each of these SiO4 units share two oxygen atom with other SiO4 units, then one type of structure that can form is a ring structure. So rings can form when two O atoms are shared by each SiO4 tetrahedra. So the formula or generic formula of such cyclic SiO4s, cyclic silicate minerals formed by sharing of two oxygen atoms per SiO4 tetrahedra is SiO3N2N minus. This is the generic formula of cyclic silicates, and we have cyclic silicates where 3 SiO4 units are condensed together by sharing of two oxygen atoms per SiO4 units, as well as 4, as well as 6, and then 8. So these by condensation of SiO4 units, that is 3 units, 4 units, 6 units, as well as 8 SiO4 units, the cyclic silicate structures are known, but only the most common here are where there are 3 SiO4 units, as well as where there are 6 SiO4 units. So these two types of cyclic silicates are most abundant. So what we have, or we can see examples where Si3O9 6 negative. So this is calcium 3. This is one example of cyclic silicate where there are 3 SiO4 units are present, and we can draw the structure of this silicate mineral or cyclic silicate mineral formed by sharing of two oxygen atom per SiO4 unit. In this way, what we have seen here, there are three SiO4 units are present over here, and each of these SiO4 units essentially share two oxygen atom with with two nearby SiO4 units. So here, what we see that, say for example, for this SiO4 unit on top over here, it shares these two oxygen atoms. Similarly, for this particular SiO4 units, these two oxygen atoms are shared with neighboring SiO4 units, as well as for this particular SiO4 unit, we see it shares this oxygen atom as well as this oxygen atom with neighboring SiO4 units, and that is how this Si3O96 negative uh, cyclic silicate structure is essentially formed, and this is an example of such cyclic silicate. So the other common examples of cyclic silicate we have said is where there are 6 SiO4 units. So the formula is going to be Si6O18 12 negative. This is going to be the formula, and examples of such uh, such cyclic silicates is where we have beryllium 3 Al2 Si6O18. So this is going to be equal to 6, and this also 6 plus here, and this is the silicate ion is essentially 12 minus. So this is what is beryl, unlike what I have said earlier, that this sort of minerals, autosilicates, this is what I have said earlier, which is wrong, that M2, M3, SiO4, that this sort of these minerals are essentially known as beryl. This is what I have said in the initial part of this lecture, but no, these are essentially known as garnets, and these are also used as gemstones. But this is what is beryl, and because this contains cyclic silicate structure, and again, but I will repeat that beryl containing 1 to 2% chromium are essentially known as emerald. So that is a mistake that we have said in the initial part of the lecture here. Garnets are autosilicates, while the beryl and emerald, they have same structure and they have cyclic silicate structure. And only difference between beryl and emerald is that in case of emerald we have 1 to 2% chromium impurity is present. So what we see is we can also draw the structure of this Si6O18 12 negative ion, where there are 6 SiO4 units are essentially condensed together. So this is how this Si6O18 12 negative ion is formed. Again, a cyclic silicate structure we see, and for each of the SiO4 units here again, they share 2 oxygen atoms per SiO4 unit here. And again, in case of beryl, the structure, if you look, then the Si6O18, these cyclic structures are essentially stacked one over the other here, and this essentially forms a hexagonal channel is in case of beryl. This hexagonal channel because the Si6O18 ions are stacked one over the other here in the beryl structure. So these hexagonal channels are present in beryl, and in these hexagonal channels we have different metal ions can be accommodated here. Different types of metal ions are reside within the channel itself, and also because of this channel here, beryl or emeryl, both they are permeable to gases. So gases can pass through because they can penetrate through this. They can go through this channel, which is hollow, and that is why these minerals are essentially permeable to gases, and gases can pass through these silicate mineral structures essentially. So we have seen how cyclic silicate structures can be formed by sharing of 2 oxygen atoms per SiO4 units. Now we will see other types of silicate structures as well. These are known as chain silicates. And again, in case of chain silicates also, like the cyclic silicates, the number of oxygen atoms shared by each SiO4 unit is equal to 2. Chain silicate structures can form if 2 oxygen atoms are shared per SiO4 units. And that is why the formula of such simple chain silicates, let us call them as simple chain silicates, because we also have other types of complex chain silicates as well. We will discuss about them later. Now, in case of these simple chain silicates, each of these tetrahedral units essentially share 2 oxygen atoms, but when they share it with other SiO4 units, each of these SiO4 units share their oxygen atom with 2 different SiO4 units essentially, and that is why it leads to formation of chain silicate structures, not cyclic silicate structures. So that and the formula of these chain silicates or simple chain silicates is essentially again similar to the formula of cyclic chain silicates, and these chain silicates or simple chain silicates, which are formed by sharing of oxygen atoms, 2 oxygen atoms per SiO4 units, essentially are known as pyroxenes. And examples of such chain structures we will see, but before that, what we should learn is that the arrangement of these SiO4 units in space may vary depending upon the mineral, and that is why depending upon this arrangement or the kind of arrangement is present, different types of structures are possible. And when the repeating units, or when the same type of SiO4 unit appear actually after how many units essentially decides the kind of structures, and the most common here is where SiO4 unit of the same type appear after every alternate SiO4 group. So we will draw the structure for such chain silicates where same type of SiO4 unit to reappear alternatively, that is after every SiO4 unit, after every 2 SiO4 unit. So this is how what we see is that this SiO4 unit is turning towards, the triangle is downward over here, and in this case it is upward. And again, what we see, the next downward is appears after two SiO4 units, and this is the most common type of Saint silicate structural arrangement in Saint silicate. So we can go on drawing in this way the structure of Saint silicates, and these are formed by sharing of two oxygen atom per SiO4 units, but they share the oxygen atom with two different SiO4 units, and that is why it leads to formation of chain silicate structures here. And the examples of such chain silicate structures are essentially two. So two it is here. Similarly, we also have Ca3SiO3 6 3. So this type of chain silicate structures we have. Simple chain silicate structures or pyroxenes we have. So with this, let me conclude this lecture over here. What we have discussed during this lecture are about different types of silicate minerals. We learned that silicate minerals essentially constitute 95% of Earth's crust, because all the rocks or the aluminosilicates as well as the clays and the sand and soil, these are all constituted by silicate minerals essentially. And many of these construction materials like granite, bricks and cement, these are also silicate minerals. And apart from that, the glass or ceramic are also composed of silicate minerals. So they have a lot of application. Then we have learned about the uh, the soluble silicate minerals, and that is about sodium silicate, which is soluble in hot water. And we have learned that it has industrial application because it is used in the production of liquid detergent, and it increases the pH of the medium, and this allows to dissolve grease and fat present in dirt. So that is why it is used in liquid detergents. Then we also learned about insoluble silicate minerals, because majority of silicate minerals are insoluble, and we learned that based on their structural analysis, several key points are can be learned, and some of these are that the electronegativity difference between silicon and oxygen is such that this SiO4 bond is essentially 50% covalent and 50% ionic in nature. Then we have also learned that these silicate minerals can be formed either by discrete SiO4 4 negative ions or by formation of polymeric or polymerization of this SiO4 4 negative ion by sharing of the oxygen atoms present in the corners of this SiO4 4 negative tetrahedral. And then we have also learned that these structures essentially are the oxygen atoms form structures which are close packed in nature, and that is why there are octahedral as well as tetrahedral holes in these silicate minerals, and different metal ions can occupy these octahedral or tetrahedral holes depending upon the size of that particular metal ion. And then we have learned about different how we can classify different types of silicate minerals depending upon the structure. We discussed about the orthosilicates, where discrete SiO4 units are present, and we have seen that there are three different types of orthosilicate minerals are known essentially, where one where divalent metal ions are present and one where the tetravalent metal ions are present. One example of this class we have learned is zircon, which is a gemstone and which looks like a diamond. And then there we learned also about another class of orthosilicates, where there are both divalent as well as trivalent metal ions are present, and these are known as essentially garnets, and these are again used as gemstones. Then we have learned about the cyclic silicates, and we have learned no, sorry, we learned about pyrosilicates, which are formed by sharing of one oxygen atom per SiO4 unit, and we have also learned about one example of such pyrosilicates, that is formed by scandium 2 Si2O7. Then we have also learned how to draw the structure of these silicate minerals or extended silicate minerals by drawing the SiO4 unit, and how we can connect different SiO4 units by sharing of these oxygen atoms, and that is how we have drawn the structure of the pyrosilicate ion initially, that is the Si2O7 ion, O7 6 negative ion, and then after that, we have discussed about the cyclic silicates, which are essentially formed by sharing of two oxygen atom per SiO4 4 negative unit, and we have learned that the cyclic silicates containing 3 SiO4 units as well as 6 SiO4 units are most common structural types, and we have also looked at two different examples of such silicates, cyclic silicates, or we have as well as drawn the structure of these cyclic silicates formed by 3 SiO4 units as well as 6 SiO4 units, and we have given the examples of different types of different such minerals, and we have one example where there is this 6 SiO4 units are present is beryl, which is essentially where metal ions are beryllium and aluminium, and beryl is used as a gemstone, we have learned, and beryl containing 1 to 2% chromium is known as emerald, which is also a popular gemstone. Then we have learned that these Si6O18 12 minus ions present in these cyclic silicates essentially are stacked one over the other in case of beryl, and that is how there are hexagonal channels are present in beryl, and in these hexagonal channels the counter cations, that is the metal ions, can be present, as well as because of these hexagonal channels, beryl as well as gemstone, they are quite porous in nature, and different gases they are permeable to gases, so gases can pass through these structures. After that, we discussed about another type of uh, silicate structure, which is essentially formed by sharing of two oxygen atom per uh, tetrahedral SiO4 tetrahedral units, and these are known as chain silicates, which have same empirical formula like the cyclic silicates, and we have given two examples of such as chain silicates, as well as what we have learned is that depending upon the arrangement of the SiO4 units in space, the structure of these chain silicates can be different, and we have learned that depending upon after how many SiO4 units the repeating unit essentially the SiO4 unit having the same arrangement reappear, the structural types are going to be different. So, and we have learned that we have drawn the structure of one such same silicate where the SiO4 unit essentially appear after every two uh, SiO4 units in the chain structure. So with this, let me conclude this structure the lecture. We will discuss more about other types of structural other structural types of these silicate minerals in the next lecture. Till then, let me thank you very much, and I look forward to see you in the next lecture.